I'm very glad to be here to see many of you are interested in this topic. And I think this is a very good excuse also for me not to do babysitting today. So today I want to talk about this deep learning for recommended systems. You know, nowadays we have this so-called information overload problem. So we have too much information available every day. So we have hard time to choose what to buy, what to watch, and what to read every day. There's so much information. There's a very well-known journalist once said, it is not information overload problem, it's a filtering failure. Okay? So we need very good computational tool to help us to filter information. Okay? You know, the search engine is a very good way for us to locate relevant information. Okay? And recommended systems is another way. Okay? So in search engines, it's a more passive way. So the users have some explicit information needs in mind, and then the system get the needs through the query, and then the search engine can return a list of relevant results to the users. So in recommended systems, it is more automatic. So the users don't need to put any explicit query in the system. So the recommended systems can automatically figure out users' interest based on the user's past interaction with the system. So in some sense, it's more useful in some scenarios. And nowadays, recommendations are everywhere, like Amazon, Netflix. So the recent articles shows that Amazon has integrated recommendations into nearly every part of their purchasing process, from product discovery to checkout. Okay? And Amazon is also one of the pioneers in this domain. So back to late 1990s, so they invented clever filtering to recommend books to their users. And Netflix also heavily rely on recommended systems. A recent statistics show that more than 80% of hours streamed at Netflix, they are influenced by their recommended systems. Okay? So the users just need a few seconds to get something really interesting to watch, and it directly impacts the user's excitement and the engagement. So it's very important for Netflix. And also recommended systems, they are pervasive in many other web services like Facebook, Google, Pandora, and YouTube. So a recent statistics show that 60% of watched videos, they came from YouTube's homepage recommendations. Okay? So it's really, recommended systems drives a lot of engagement in those websites, services. So on the other hand, the deep learning has been emerging. So everybody knows that deep learning has shown very impressive results across a wide range of applications. Okay? So first of all, what is deep learning? Okay? So here I have a simple definition. Okay? Sorry, you cannot see the slides. But so here I highlight those keywords in deep learning, like nonlinear. So deep learning is about a nonlinear transformation. They can capture very complex relationship and the subtle patterns from the data. And also, it's about learning representations of the data. Okay? So the users don't need to manually craft features. Okay? So we can automatically learn features from the data. Okay? and those features usually the high-level features. So what is deep learning not about? Okay, here I list some points. So deep learning is not about AI, especially it's not really like strong AI. Okay? It's a very specialized machine learning technique. Okay? It's a very small subset of machine learning, and machine learning is also a subset of AI. Okay? So AI has many to deep learning than just machine learning. Okay? So the deep learning is not the artificial equivalent of the human brain. Even though some techniques in deep learning are inspired by neuroscience, but the way we construct deep learning models, actually they are very preliminary. So compared to the complexity of our human brain, so there's still a huge gap. Okay? So deep learning is not even the best tool for every machine learning task. Okay? It is useful for many tasks, but actually it's not for all the tasks. Okay? It has some limitations. For example, it requires a lot of data to work well. Okay? If in your domain, your applications, you don't have a lot of data, the deep learning very likely will fail. Okay? And also, it's very computationally expensive. Okay? So nowadays, we rely on GPU to train a good deep learning model. So compared to traditional machine learning models, it's more computationally expensive, and there's no theoretical guarantees. Okay? So the theory is far behind the applications. Okay? So we have seen many successful applications, but we don't have a really good theory behind those results yet. And it's mostly a black box approach. It's very hard to interpret the model, those intermediate layers, so that it's very hard to explain why deep learning model works. Okay? So there's a lot of pitfalls in deep learning. So when we apply deep learning, we need to be careful. Now I want to just give you a very brief introduction to deep learning. Okay, so first of all, what is neuron? Okay, so a neuron is just a nonlinear transformation of your data. Right? So it takes a linear combination of your input features, and then it applies a nonlinear activation function. For example, the sigmoid function. Okay? And then to generate a output. Okay? That's one neuron. Okay? So in the basic feedforward multi-layer neural networks, so there are many layers, okay, many layers. So each layer, they do such nonlinear transformation, okay, of the input, okay, and then feed the output as the input to the next layer. Okay. And so overall, you can view deep learning models as a very nonlinear, complex transformation of your input, okay, to generate output. Okay. So in the learning process, we want to learn those weights associated with each transformations at each layer. Okay. So they are the weight parameters we want to learn. Okay. So how can we learn those parameters? Okay. So we can use so-called gradient descent techniques. Okay.
Excuse me, point of order, please. There's limits as to how many of us can simultaneously connect to the internet. So if a few people have it, would they mind identifying themselves? The rest of us can cluster around it so we can see your slide. Who's online? Perhaps we can cluster around these.
Notify the people online. I think they're all one. Yeah. So your mic is active, right?
Yes.
We'll just start in another minute if we can mention it. That way your voice will go.
Hi.
Problem with the HTML issue. I have HTML. If you want to connect.
No, I think there's a problem with the we tried to make it.
Yeah.
So you have HTML.
Yeah. Yeah. This is the systems problem.
Both on the HTML, we have everyone has it.
Okay, so yeah, I'm really sorry. This is very special experience for me, and I've never teach a class in such a way. Only I can see the slides. Okay, so so the general techniques to estimate parameters in machine learning models is to using gradient descent, okay, to minimize the loss function of your model. Okay. For example, in linear regression, okay, so the loss function is a least square of the errors. So here F is your prediction based on the linear function. Okay. So Y is a ground truth value. So we want to approximate the ground truth value as much as possible. Okay. So once we write down this loss function, and then we take the derivative of the loss function with respect to the parameter W. Okay. And in each step, we go move our value to in the steepest descent direction, so that we can approach the minimum of the object function. Okay. So that's a general technique. So actually in deep learning, we apply the same technique to estimate parameters. So the only difference is now F is not a simple linear function. So F is a complex nonlinear function, okay, produced by these layered neural networks. Okay. So this F looks like, okay, it's a nested functions. We apply nonlinear functions multiple times. Okay. So overall, it can view is a highly nonlinear transformation. Okay. But the way we estimate parameter is the same again. So we have write down the loss function and then take the derivative of the loss function with respect to the parameters W. Okay. So there's a well-known technique, so-called backpropagation. So the backpropagation is just a gradient descent algorithm with the dynamic programming, because this F function is a nested function. Okay? So when we derive the gradient, we have to apply the chain rule. Okay? At the chain rule, and those you'll see that the gradient, some intermediate result, can be cached so that we can use that multiple times. We don't need to recompute those gradients. So that's the major idea behind this backpropagation. Okay? So they will store those intermediate gradients when they estimate the overall gradient. Okay. Yes.
Can you also share the slides on Google Drive or something so that I can just forward the link to the people who have interest on this?
So you mean I can send the slides to your email? Do you want?
Yeah, I'll upload it and send it on.
Do you want me to now, right now?
If you can do, because there are a lot of people who are confusing the time.
Okay.
You have the USB?
Yeah, I have the USB. So how many of you already know deep learning? Okay, I think I can move faster. Okay. So so this backpropagation algorithm is actually not new. So it was actually reinvented multiple times. And it didn't really work well like 30, 40 years ago. Okay? That's why we experience so-called neural winter. Okay? And these early neural networks didn't deliver very good performance, and the results were disappointing. Okay? So the people started abandoning the field. Okay? And also there's very low funding in this area. Okay? So the area was revived in the mid-2000s by so-called layer-wise training. Okay? And the deep learning boom has really started around 2012, okay, when the AlexNet achieved much better results in the ImageNet challenge. Okay, in 2012, there's a significant drop in the error rate, okay, on ImageNet achieved by AlexNet. Okay. So the same phenomenon was observed on speech recognition test. Okay. So we see around like 2014, there's a significant improvement, okay, in speech recognition, okay, achieved by deep neural network models. So people might be wondering why we want to do deep learning for recommender systems right now. Okay, so there are several reasons. So first of all, the availability of big data. Okay. So deep learning models, they are complex nonlinear models, so they need a lot more data to train. Okay. And nowadays, we are gathering a huge amount of data, okay, in many domains, okay, and also in recommender systems. So we get a huge amount of user interactions with the recommender systems. Okay? So so that we can apply very complex deep learning models now. Okay? And so this graph shows that how different models scale with respect to the amount of data. Okay? So as you can see that, so the traditional machine learning models, when you increase the amount of data at the beginning, the performance of the model also increased. Okay? But at a certain point, the performance get flattened. Okay? Even if you increase a lot more data, so the performance will not really get better. Okay? But the deep learning model, especially very large or very deep neural networks. So when you increase the amount of data, and you can see the performance of those deep learning models continue to increase. Okay? So that's a very nice property, because when we get more and more data, now we can further improve the performance of our algorithms. Okay. So another reason why we want to do deep learning right now is because of the compute, especially the GPU technologies. Okay. So the neural network and deep learning models rely on matrix and vector operations. Okay. So the GPU architecture is a very good fit. Okay. So in terms of research breakthroughs, okay, compared to 20 years ago, so now we have invented good techniques so that we are able to train very deep neural networks. Okay. First of all, we have a non-saturating activations instead of saturating activation functions such as sigmoid or tanh functions. Okay, so if we look at those traditional activation functions, so they are squeezed in the range. For sigmoid, for example, is between 0 and 1. Okay? And so these non-saturation activations, such as ReLU, Leaky, ReLU, so they will, when you, for example, look at the x, okay, when x goes to infinity, okay, so the transformation will also goes to infinity. Okay? So it's avoid gradient saturation problem. Okay? And also we have a dropout technique so that we can regularize our network. Okay? So the dropout is a very simple technique that we randomly disable certain units and their associated weights. Okay? It's like ensemble learning, because now you have a multiple configurations of your networks, and later you average them. So it's a form of ensemble learning and also a form of regularization. That's why it works pretty well in practice, even though it's very simple. And also we have a mini batch, okay, technique, so that we can get the best of the both worlds of full gradient descent and stochastic gradient descent. So the full gradient descent is very costly. Okay? It's very costly because you have to compute the gradient by looking at all the instances. Okay? But the advantage can be parallelized. So on the other hand, SGD, stochastic gradient descent, is very cheap, okay, because you only compute a gradient by using one data point, but it may require more update steps. Okay, so then this mini batch will utilize multiple data points, but not all the data points to compute the gradient. Okay. It also turns out to be a very effective technique. And another research breakthrough is we have adaptive learning rates now, like Adam data, AdaGrad, okay? So that for each parameter, you can have a different learning rate. Okay? So these techniques makes your algorithm converge faster than before. Okay? And also now we have a deep learning frameworks such as TensorFlow and PyTorch, so that we can easily implement or experiment different deep learning models. Okay, and we can do automatic differentiations, okay, without manually computing the gradient. Okay. So it significantly speed up our experiments. So why want to do deep learning for recommender systems? Okay. So there are some special characteristics in the RecSys domain. So first of all, in RecSys, we have multimedia data, okay, such as images, text, audio, video, and so on. Okay. And the deep learning techniques, they are very useful to extract features directly from those content. Okay. And it can handle this heterogeneous data very easily. Okay. So basically, we can embed so multimedia or heterogeneous data into the same latent space. Okay. And also, we can use deep learning models to model dynamic or sequential behavior. Okay. For example, by using recurrent neural networks. Okay. And we can use deep learning models to capture more accurate representations of the users and items. Okay. And lastly, the RecSys is a very complex domain. Okay. It's very complex. And deep learning has been proved to work well in other complex domains like natural language processing, computer vision. It's a recommender system. Yeah, it's a shorthand for recommender systems. Okay. So there's a community behind the RecSys. There's a conference called ACM RecSys that organized every year. Okay. So here I show the timeline for deep learning for RecSys. Okay. So the first application of deep learning to RecSys that I'm aware of is in 2007, okay, by Deep Boltzmann machine for rating prediction. Okay. So they apply this to Netflix price data set, okay, and get pretty reasonable result. But after that, there's very few work in this domain, okay, between 2007 and 2014. Okay. So as deep learning gained attraction in other domains, so starting from 2015 and 2016, so we have seen noticeable increase of deep learning papers in the research communities. Okay. So back like 3 years ago, so my group started to work on deep learning for RecSys, but we really had hard time to find relevant papers in this domain. Okay. But now we have seen exponential increase of the papers. So today I will mainly discuss 3 main topics, okay, and research directions in deep learning for RecSys. Okay. So the first one would be deep collaborative filtering. Okay. Second one is the feature extraction directly from content. The third one would be the sequence modeling for recommendations. So these 3, I believe they are the current main research directions in this field. So first of all, deep collaborative filtering. Okay. So how many of you already know collaborative filtering? Okay. There's still a few of you didn't know. So I'll just briefly go over the basic concept. Okay. So the collaborative filtering actually it is a very important technique for recommender systems. It was invented 20 years ago. So in collaborative filtering, so we observe a group of users like Alice, Bob, Kevin, and so on. We also observe a group of items, okay? And then we observe the interaction between users and items. For example, Alex may say, I like kiwis, and Bob may say, I like oranges. So based on those preferences of the users over items, so we want to predict new preferences. For example, does Bob like strawberries? Okay. So we want to predict those new preferences of the user over items. Okay. So that's the task of collaborative filtering. Okay. So we need to look at other users in order to make such prediction. So that's why we call it collaborative filtering. Okay. So there are three major approaches to collaborative filtering. Okay. First one is so-called latent factor models, which are based on matrix factorization. Okay. Second one is neighborhood-based approach. Third one is a hybrid between these two. Okay. So first of all, these latent factor models. So in latent factor models, so essentially we observe this interaction matrix. So for movie prediction, it would be a movie rating matrix. So if the user likes that movie, it will be 1. Otherwise, it will be 0. Okay. But this matrix is very sparse. Okay, because one user may only rate very few movies or items. Okay. It's very sparse. So our goal is to want to factorize this matrix into the product of the two matrices. So one is the user latent matrix M, another is the item matrix E. Okay. So each rating RUI can be viewed as a product of the user latent factor M and item latent factor E. Okay. So this M and E, they are parameters we want to learn. Okay. Okay. So the object function would be to minimize the difference between the ground truth rating RUI and our predicted rating, which are product of MU and the EI. Okay. So we want to minimize the difference. Okay. So here I show the object function. We minimize this object function. So the second terms, they are regularization terms just. Okay. So we minimize this object function with respect to the parameters, which are latent factor MU and the EI. Okay. So once we obtain MU and EI, we can then predict the preference for any user U and item I, right? We just do the dot products. Okay, we can produce any prediction. Okay. So that's the idea of latent factor models. So it's essentially a matrix factorization. So as you can see, these latent factor models, it is essentially a linear model. So we approximate the observed rating RUI by just a simple dot product of MU and EI. Right? So a straightforward extension by using deep learning is we can model their interactions in a nonlinear way, right? Or we can learn a nonlinear representation of the users or items. Okay. So here I have two approaches. So one is so-called representation-based learning. So each user can be represented by using neural networks. Okay. So those latent factors for the user can be learned from a neural network instead of a linear function, right? So similarly, the item can also be learned by using a nonlinear neural network, okay? And their interaction could be another neural network, okay? So this interaction learning as you can see, the interaction can be modeled by another nonlinear neural network instead of just a linear dot product, right? So that's a straightforward extension by using deep learning model. So there's a very well-known work. Just the basic idea is just exactly what I just described. Okay? So instead of just use a linear function with dot product to model the interactions between user and item, so we use a neural network. Okay? And the user latent factor and item latent factor can also be learned from another two neural networks, respectively. Okay. So this model is called neural collaborative filtering. Okay. So that's a straightforward extension or application of deep learning to latent factor models. Okay. So another type of model is based on autoencoders. Okay. So in autoencoders, so we have a neural network, right? But now the input of the neural network and output of the network would be the same. Okay, so the goal is to reconstruct the input data as much as possible. Okay, so once we have learned this neural network, we then can using the hidden layer as a representation or latent factor for our input data. Okay. So this is a so-called autoencoder. Okay. So you can prove that. So autoencoder is if you assume all the activation function are linear, is essentially equivalent to matrix factorization or PCA in some sense. Okay. So that's why you can apply this autoencoder to learn the latent factors, okay, in a nonlinear way, right? In a nonlinear way. So here is a representative work by using AutoRec. So they call the technique AutoRec. It's essentially applying autoencoder to learn latent factors. Okay, so here the input would be the items. Okay. Items, and each node is the ratings by the corresponding users. Okay. And then we want to reconstruct this input. Okay, so the output would be the same as the input. So the intermediate layer would be the latent item representation. Okay. So the object function is the reconstruction error, as you can see. And the second term, again, is just a regularization term. Okay. Again, so this kind of approach is essentially doing matrix factorization, but in a nonlinear way. So even though autoencoder only have one hidden layer, but the activation function is nonlinear. So it will learn some nonlinear relationship. Okay. So another representative work is called collaborative denoising autoencoder. Okay, so it's overcome the previous autoencoder problems. Okay, so one major problem with traditional autoencoder is it may learn some trivial functions like identity functions if you make input and the output are exactly the same. Okay, so in denoising autoencoder, you will corrupt the input. Okay, just add some small noise so that you'll not learn those trivial functions. Okay, so that's what this paper do. Okay, it's essentially to apply the denoising autoencoder. Okay, to learn the latent representation of the items or users. Okay. So our group also did some work by extending denoising autoencoder using attention mechanism, okay, by utilizing the contextual information. So, you know, in recommendation problems, sometimes you have some extra information available, like the location or the time of the day. So those extra information may help you to make better recommendations. Okay, so we use this so-called attention mechanism to model those contextual factors, so that we get a further improvement. So today I'll just quickly give a very big overview of the field because of the time constraint. So if you are interested in a particular part of the talk, so we can always talk offline. Okay. So this work is called a wide, deep, and deep network proposed by Google for their Google app recommendations. Yeah. So you can view traditional machine learning models. They are wide models, which means they have a lot of features, but you usually just have one layer of transformations. Okay, for example, for logistic regression, you just take a linear transformation of the features, okay, and then apply sigmoid function, and then produce the output probabilities. Okay, and because you have many features, so your model is very wide. Okay, so the deep learning models usually they are very deep. Okay, so you only just apply one layer of transformation, you apply multiple layers. Okay, so it will be very deep. Okay, like in computer vision, some of the models have more than 1,000 layers. Okay, so this work kind of combine this wide and also deep networks. So half of the networks they are wide, okay, and another half they are deep. Okay, so here is the exact architecture. Okay, the exact architecture. So they have the left-hand side. So those features, they are very deep because they have to go through multiple layers of transformations. The right-hand side of the layers, they are wide, okay, because they directly feed to the output. Okay. So it's try to get the best of the both worlds, the wide model and deep models. So in the experiments, it shows that the deep model achieved about 2.9% improvement over wide model. And by combining the deep and wide, it's achieved about 3.9% improvement over wide models. Okay. So the next work was also done by Google for YouTube recommendation. Okay. So you know YouTube nowadays has do a lot of recommendations. Okay. So in their architecture, so they have two steps. Okay. So one step is to generate the candidates, okay, of the videos, okay, because they have like millions of candidates, okay, at the beginning. So they want to only select a much smaller set of candidates, okay, and then to feed to the next step to do more fine-grained ranking. Okay, so in the first step, so they will extract about hundreds of videos as a candidate from millions of videos, okay, in their set. So in the second step, so they will re-rank those hundreds of videos and then only show dozens of videos to the user. Okay. So in this way, they have a trade-off between effectiveness and efficiency. So the first step is usually a very efficient model, okay, by only looking at a smaller set of features. Okay, so that's the left-hand side of this slide. Okay, and the right-hand side is a deep ranking model. Okay, so the architecture between these two, they are similar, but the features in the second step is much more than the first step. Okay. So they also achieve a very good result, have very good trade-off between efficiency and effectiveness. Okay. So it's a very well-written system paper. So if you want to know the tricks and how to make recommender system scalable, I highly recommend you read this paper. So the architecture-wise is not very complicated, okay? But I think they apply lots of very useful heuristics, okay, to make it scalable, to handle millions of videos. So as I mentioned, the second major type of models is called neighborhood models. Okay, so in neighborhood models, the key idea is to find similar users. Okay, so the assumption is similar users will like similar items. Okay, so if you can find similar users, and then we can use those similar users preferences for prediction. Okay. But that's a neighborhood approach. Okay. So our group proposed so-called collaborative memory network. Okay, so it's based on memory network. So in this architecture, we combine the latent factor models and the neighborhood models. Okay, we combine these two classic collaborative filtering techniques. So the memory networks is a extension to attention mechanism, okay? And it has achieved very impressive results on natural language understanding. Okay, so I will skip the technical details of this model. So in the paper, we have shown that the relationship between our model and the existing models. So we have shown that the traditional models, they are just a special case of our model. For example, by dropping certain terms in our model, okay, so you'll get the traditional matrix factorization model. Okay, so by dropping other terms, you'll get traditional neighborhood model. Okay, and also you can get hybrid models by simplifying certain terms. Okay. So this work just gives you a unifying understanding of different models. Okay, and also what's the relationship between traditional collaborative filtering models and today's deep learning models. So we have done many experiments, have shown that this model achieved the state-of-the-art result on several data sets. Okay, so that's the first direction, which is deep collaborative filtering. It's basically extend the traditional linear collaborative filtering, okay, by using neural networks so that we can capture complex interaction between user and items. So the second direction would be feature extraction from content. So in many recommendation domains, in addition to the interaction data, okay, we also have a content data available. For example, for products, we may have the description of the product. For users, we may have the profile of the users. Okay. How can we utilize those content information? I think the deep learning models, they are very useful here because deep learning models, they are very good to learn representations from content, right? For example, if your content data, they are images, so you can apply CNN, convolution neural network, okay, to learn the representation. If your content is text data, you can use a recurrent neural network to learn the representation. Okay. So there are three ways in general to utilize those content information in collaborative filtering setting. Okay. So first one is to use the representation we learned from deep learning model as the initial latent factor model, as the initial values for latent factors. Okay. So, you know, even the latent factor models, they are, if you look at the object functions, they are non-convex, which means if you use different start initial values, okay, you may get different results. Okay, so we should use good initial values. Okay, so one way to get a good initial values for the latent vectors is to use deep learning models to learn those latent factors from the content. Okay, and use those values to initialize the latent factors. So the second way is to use those latent factors we learn from content to regularize the latent factors we learn from feedback matrix. Okay. So the third one is to do a joint learning, or we call it end-to-end training. Okay. So that we learn everything in a unifying framework. Okay. So so one representative work is to use publish at ICCV, Computer Vision Conference, by using convolutional neural network, for example, AlexNet, okay, to extract deep image features. Okay, and then we do a linear transformation of those image features. Okay, okay, as a latent factors for the images. And then we do the dot product with the user latent factor and then produce the prediction, okay? Produce the rating, so YUI here. Okay. So the parameter here is the W here, the linear transformation, and also the weights in the convolutional neural network. Okay. So we can train the whole network in an end-to-end fashion, okay, to learn W and F. Okay. So another work is to apply a convolutional neural network to music recommendation. Okay. So first of all, we can represent those music data by using so-called time frequency representations. Okay. Or TFCC, okay, sorry, MFCC, okay. So it's kind of like a 2D data, so that's why you can apply CNN, okay, to those data, okay, to get the latent representation for those music, okay. And then, so once we get those latent representation, and then we can multiply with the latent factor of the user, XU, and then to produce the predicted rating, PUI. Okay. So here we have two separate steps. So the first step is to learn the latent factors from the content of the songs, from the music. Okay. So once we learn that latent factor, YI prime, so we plug into the traditional latent factor model, okay, and then we can learn X mu. Okay. So the benefit doing this way is we can overcome so-called cold start problem. So what is cold start problem? So this is a very pervasive problem in recommender systems. Okay. So you know, a lot of times we get new users and new items. So for new users and new items, we don't have any information, right? We don't know what these users' ratings or preference, okay, on the existing items. Okay, how can we deal with those new users and new items? So this is called cold start problem. Okay. So so one way to deal with cold start is by looking at the content information. Okay. So we don't have the interaction information of for new users and items, but we may have the content information about the users or items. Okay, we may know the description of the item, or we know the profile of the users. Okay, so we can then learn the latent factor representation from those content information. Okay, so that use that we can make predictions. So we also published a paper by proposing this so-called neural semantic personalized ranking. Okay, so here this DJ here, they are the content representation of the item. So they are the, for example, the back of words representation of the items, and then we apply the deep neural network to get the latent representation of those items from the content. Okay, so this V, this Y, the latent factor we learn from the content, and this V, they are the latent factor we learn from the interaction matrix. Okay, the ratings or clicks, for example, and then we want the latent factor we learn from content, they are as much as possible, as close as possible to the latent factor we learn from the interaction matrix, VJ. Okay. So so here we use so-called pairwise ranking. Okay. So these are J plus and J minus. So J plus is the item that we preferred over the item J minus. Okay. So as you can see, we learn these both latent factors of users and items in a joint fashion, end-to-end framework. Okay, so that we can overcome the cold start problem. Okay? For the new user, for the new items, for example, we can learn the latent factors from the content information. So the last direction in this domain is sequence modeling for recommendations. Okay. So the recurrent neural network is very good to model sequence, right? So they can model, for example, natural language. Okay, by looking at the context of a sentence, they can predict the next word. Okay. So there are three types of recurrent neural networks. So one is called sequence to value, which means the input is a sequence, the output is a scalar. Okay. For example, the sentence classification, right, would be such case. Okay. So the input is a sentence, is a sequence of words. So the output is a label. For example, whether the sentiment of the sentence is positive or negative. Okay. The second class is a value to sequence. Okay. So the input is a value. Okay. The output would be a sequence. Okay. So with this model, we can generate the sequence. Right. So for example, the image captioning, right? So given the image, so we can generate the caption of the image, which is a sequence of the words. So the last one is a sequence to sequence model, right? So we usually use so-called encoder-decoder architecture. Okay. So an example is machine translation. Okay. So in machine translation, both input and output, they are sequences. Right? The input is, for example, a sentence in English. The output is a sentence in Spanish. Okay, and we can use two RNNs to as encoder and a decoder. Okay, to model such problems. Okay. So those are the three types of recurrent neural networks. Okay. So a major issue with recurrent neural network is the gradient exploding or vanishing. Okay. Because this neural network is in general they are deep, right? If your sequence is long, okay. So there are several ways to alleviate this issue. One simple way is just applying gradient clipping. Okay, if the gradient is too large, we scale back. Okay, the second way is to use identity function to do the transformations. Right. Okay. So when you have very deep neural network, right? So when you apply multiple transformations, okay, so you may get gradient exploding. Right? But if your transformation is identity function or very close to identity function, so your transformation will not change your data too much. Right? So that's the idea behind this identity RNN. Okay. Or we have more sophisticated architectures such as STM or GRU or some of the variants. Okay. So we can apply these sequence-based models for recommendations. Okay. So in recommendations, sometimes we observe a session, right? So in a session, a users may purchase multiple items, or they may click on multiple items, right? So such behaviors, they must have some time dependence, okay, in this in a session. So we can use these sequence-based models to model this dependence. Okay. So for example, the task would be the next click prediction. So based on the previous clicks, okay, so whether you click or items you click on the next item. Okay. So we can apply this GRU. So the GRU is just a simplified version of LSTM. Okay. So the input is the actual items you have to click on. Okay. So it is a one hot encoding, and then we have embedding layer, okay, to embed each item, and then we have this GRU layer to model the dependence of the items in your session, okay, and then we finally will generate the scores on the candidate items, okay. So how likely they will click on those candidate items. Okay. So this paper applied GRU for recommendations with two modifications. Okay, so one modification is they use so-called mini batch, but at a session level. Okay, so in a traditional way doing mini batch for RNN is you look at the instances within a sequence. Okay, but in this session, in a session, user may only click on very few items, let's say 2 items. In other cases, it may click on like hundreds of items. So it's a very large variance. Okay, and this paper, they instead of look at the in-sequence clicks, they look at the cross sessions clicks. Okay, so that's one modification. Second one is they use pairwise loss function instead of a pointwise. So the last work I want to talk about is called a context-aware citation recommendations. Okay. It's from my group. So the task is to recommend the reference to cite when you write a research paper. Okay. So you know, when we write papers, we also want to find the relevant papers references to cite. So this work will automatically recommend the candidate reference to cite given the context, okay, of that citation. Okay. So this problem can be formulated as a sequence-to-sequence learning, right? So this input would be the context, okay, the context. So what you wrote before this citation, and then the output would be the cited paper, right? And we propose this so-called neural citation network for this task. Okay, similarly, it's an encoder-decoder architecture, but instead of using RNN as encoder, we use CNN. So actually, CNN can also be used to text data, right? So CNN is usually for images for 2D data, okay? But it can also apply to 1D data, like text sequence. And the decoder is a GRU, okay? And in between, we also apply the attention mechanism so that we can capture the influence of the authors, okay, on your citations. So there are also some other deep learning work for recursives. So for example, recently people applied deep reinforcement learning for recommendations. Okay. Also apply adversarial network, like again, for recommendations. Or they do the hybrid models, like CNN combined with autoencoder, CNN combined with RNN, RNN combined with the autoencoder, RNN combined with the deep reinforcement learning. Okay, so you can take arbitrary combinations of the techniques I talked about before, so you can have a new architecture. Okay. So the potential limitations of deep learning for recommender systems is, first of all, it's very hard to interpret your model, right? So this is a common problem with deep learning, right? It's very hard. But we do want our results are explainable, right? So that's just to enhance the trust of the users, right? For example, so Amazon has just a single line explanation of their results. The users who bought these items also bought the following items, right? So they have this a simple explanation of their algorithm so that people will more trust their recommendations. Okay. So if everything of your algorithm is a black box, it's just make users less trust of your recommendations. The second problem is deep learning models, they are data hungry, right? They need a lot of data to train. But in some domains, we may not have a lot of data available, especially if we only look at the interaction between users and items. Okay, so usually those interactions, they are very sparse, right? So one user only look at few items. Okay, they are not able to look at all items. Okay, even though the matrix is huge, but the interactions, they are sparse. Okay, so the deep learning models may not work well in those cases. So lastly, the deep learning models require a lot extensive hyperparameter tuning. Okay, it's actually tricky to make it work. Okay, sometimes even you just set a wrong batch size for mini batch, so you may not get your algorithm converge. Okay, sometimes it's tricky to make it really work. So here I list some best practices. Start with something simple, simple architecture, and then incrementally improve it, so make it more sophisticated. Okay. Optimize your code, okay, to make it more efficient. Okay. And also consider scalability. Scalability is a key. How your algorithm can scale to a large number of items. And open source your code. And experiment on public data sets, okay? So that you can have a comparison with the existing work. And don't use very small data sets. Okay? As I mentioned, the deep learning model may not work well on small data sets. Okay? And also work on more relevant tasks than rating predictions. Okay? So deep learning actually open new doors to new tasks. Okay? by using, for example, multimedia information, right? So we need to explore new tasks instead of using deep learning as a new tool to solve existing tasks. So in conclusion, so deep learning is now in RecSys. Okay, so there's a huge potential, but there's still lots to do. Okay. So today I introduce 3 research directions in this field, but there's actually a lot more going on. Okay. The scalability should be always kept in mind. Okay. And so lastly, don't fall for the hype, but don't disregard the achievement of deep learning and its potential for RecSys. So here I list some future directions. So first of all, how we can make explainable recommendation. So as I mentioned, it's very important to make our recommendations, our algorithms interpretable. Okay, interpretable. So this attention mechanism, actually, I believe is one direction. So you know that attention mechanism has been used a lot in computer vision. So the idea is we can, instead of looking at the whole images, we can focus on the important part of the image. Okay. So the same idea can also apply to recommender systems, so that we can better understand the inner workings of our algorithm. Okay. So secondly, how can we go deeper? Okay. So if you look at today's deep learning model for recommender systems, they're in general not very deep, right? Mostly just 4 or 5 layers. That's it. So compared to in computer vision, like they have like over 1,000 layers. So it's much shallow. Okay. So we have difficulty to train deep, very deep models for RecSys. Okay. So next, the question is, how can we make our model deeper for RecSys? Okay. So that we may even gain better result. So third direction is transfer learning for recommendation. Okay. So transfer learning has achieved impressive performance in many other domains. For example, in the recent natural language processing, the BERT model proposed by Google, so they train their model on a huge corpus, like on a whole Wikipedia corpus, plus the Google book corpus. Okay, and then they just need to fine tune their network on a small data set in the particular domain. Okay, so that they can transfer the knowledge from a very large corpus. So how can we do this transfer learning for recommendation? So it's I believe that's an important direction. Okay. For example, how can we do recommendation across different domains or across different tasks even, right? For example, how can we do profile or item classification at the same time do collaborative filtering, right? Because the latent factor we learned from collaborative filtering can also help you to classify the items properly. So how can we do this multitask learning? So I think that's an unsolved question. And also scalability. Okay? How can we make our algorithm scale to much larger data? How can we do incremental update instead of retrain everything from scratch? Okay? How can we do our training in an online or streaming fashion? Okay? Because a lot of data there, they come in stream. Okay? So with those streaming data, we can just incremental update our model so that it would be more efficient. So lastly, the benchmark evaluation. So I think in the RecSys community, we need something like ImageNet, right? So that we can do this fair evaluation in the same platform. So currently we don't have that yet. That's why you see the inconsistent results in different papers. Okay, because people split data differently, right? Even the training and testing, different researchers do it differently. They also do the processing in a different way. So it's to make the comparison across different methods very difficult. I think in the community we need something like Kaggle competition, right? So there are some hidden data sets